Welcome to today's webinar with the title News from Building Model for RFEM 6. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the German and English webinars, technical content of the website, customer projects, and so on. I will be the moderator today and I will answer your questions during the webinar. The presentation will be done by Bastian Kuhn. He's responsible for the building model add-on and also for the development of the timber design add-on. He works also in the customer support team. Yeah, and as I said, he will be the presenter. Okay, I say something how you can ask questions, at least for the attendees who participate the first time. At first, I switch off my webcam that you can see the full screen. If you have a question, then just press that button with the question mark, enter your question in that field, press send, and I will receive your question and I will answer you. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. Okay, that's at the moment all from my side. I hand over to Bastian. Bastian, it's your turn.
Yeah, thank you, Andreas, for the introduction and welcome also from my side. The content of today's webinar will be the treatment of load transfer surface in the building model, the neglecting of surface stiffness in the load transfer surfaces, and the output with the building model. Now, end the presentation and directly go into the program. As a model name, I will name it building model. I created a template on the add-ons. I already activated the special solution add-on building model. Maybe later on, I would like to define a CLT or timber frame wall surface. Therefore, I will activate also the multi-layer surfaces. I will not show the design of any material, but to show you the configurations and what input can be given to the design add-ons, I activated the concrete design and the timber design add-on. In the standards, I use the global Eurocode. Okay, therefore I will activate the model. When you start the modeling of a structure, you usually are doing this via the DXF import. It is possible via file, import, and then use the import functions, or what is even smarter is to go to guide objects and import background layers. I have a predefined DXF named story. I will change the rotation about 180 degrees to have it on the other side. I can look if I have separate layers, which is the case in here, and import it. I will directly move into the Z direction. Now, when you look for it, on the left side of this building, I will define my stiffening walls, my stiffening elements. So it goes from the left top corner to the middle corner and the bottom middle and the left bottom side. That's where my stiffening kern of the structure will be. And on the right side, I will create the facade elements. Before I'm modeling it, I have to go into the objects of the building model and define my stories. I want to define 5 stories, with each story should have a height of 3 meters. So 1, 2, 3, 4, 5. We have several options for the floor modeling. I will explain them all when we come to that, but we will start with the floor modeling nothing. So that's just an advanced output of the structure. The other modeling types, rigid, diaphragm, semi-rigid, and also load transfer, they require, or they will generate a different modeling. And then, of course, when we have rigid or semi-rigid diaphragm, we can also have different nodal support modeling and the different line support modeling. But I will show that all later on. Okay, so far nothing changed. We can move it and we see, okay, here we have the height of minus 50 meters. So that's the height of my stories, but that's in sum all. But now that I have arranged that, I can define here via this button columns, walls, and also floors, which is possible. And I already named it or said it. I want to define the stiffening elements on the left side of the building. Therefore, I will select the wall, choose the stiffness type standard, and create my thickness type uniform. There's the wall inside here, okay, and I can leave it by 20 centimeters. And I'm choosing a C2530 ordinary concrete. All right. There are objects that can be defined via the concrete, but that should be the part of a different webinar. And I will now start from the middle top corner. Also, I have to select the building stories. I will define them all. And then I will skip the window. So here's the window to be situated. You see, with the building story or with the building model add-on, there's already coming the information of the mass of my structure. So right now I define two walls or two parts of the wall, plural, and I have a complete weight or mass of 9.72 tons. And when I'm moving it out a little bit, that's not enough, but maybe we can go a little bit further in here, there. So then you see that the mass center is moving while I'm defining more surfaces. So that's an information that's already generated by the building model add-on. Okay, so I have to do this now for each of these parts in here for the complete kernel. Okay, and to this edge, to this edge. And from this to this. So my building is closed now. And you see that also the mass point or the mass center is nearly in the middle of the structure. And I already have a weight of 42 tons. Of course, it's concrete. Maybe I can also activate a few more stiffening elements. I mean, probably not necessary for stiffening my system, but when I have them, I can use them in here. Okay, and there's also probably going to be a wall that's will not be changed during the assembly on the job site. All right. Okay, so 56 tons, that's it. And now the effect of it is coming when we go a little bit into 3D rendering or it's a 3D view. So you see that because of this input, already the complete stiffening or the walls that are stiffening my system are defined and already are defined into the structure. So that's already done. So, and of course, I said it here in this case, we will need a few more posts and maybe we will put some kind of maybe a drywall or a masonry wall or something like this on this part in order to reduce the free span, because if I do not activate this walls in here, I will probably get problems with the deflection on the vibration of my structure. So I will proceed with the columns. Therefore, I will define, well, yeah, quite a bigger section inside here. So let's say we will create a new section in here and give it the dimension 275 by 275. We can use timber material here, the so-called Baubuche is the material which is perfect if you have quite a high pressure force there. Okay. And I can take a look if all stories are activated. That is the case in here. And so I will say, okay, I have probably a column in here and a column there and one on the edge here. And where else can we have one? Yeah, probably here. This. 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 Oops, that was wrong. Oh, I can just go one step back. And that's still working. Okay. And what's okay. Okay, so these are my columns. This one's actually a little bit too narrow to me. I will also undo this step. So that should be enough for this now. I can directly put a hinge on top of those columns so that they will not bear any moment transfer. So therefore I say, okay, hold on, not the walls. I only want to activate the members. Edit, and will define a hinge at the member and just a simple ordinary moment hinge. Okay, so that works. And go back into the Z direction, or maybe I will define now already the supports, at least the column supports. That is also just a hinged support here. Okay. And now for transferring the force from the facade to the columns, in former times with the building model add-on, this was not possible, as we used to integrate some kind of hierarchy to it, and this is possible now, and I want to show that to you. Therefore, I'm defining a load transfer surface with the object wall. So here in stiffness type, I will use load transfer. I'm choosing the load transfer direction isotropic FVA. There is a special webinar that is explaining completely this load transfer stiffness type, to which I would like to refer now for further informations. Okay, So the load transfer surface can be quite simple in here, from this edge to this edge and to the bottom edge. Oops. And to this point. Okay. So it's also there. And I said it here in this area, I want walls that do not stiffen my structure. They should only put the forces from the top story to the ground. So therefore, I will define again the load type wall, but with standard behavior, and create a new thickness, which is called wall shear free. The picture slightly explains this thickness type. So it can, the type thickness type wall shear free can transfer forces into the global X and Y direction of a wall of the element. I'm choosing a different material. Let's say wall not stiffening, and it of course can be a little bit bigger. Let's say we would, what do we choose in here? Let me take a look what I wanted to have inside it. Yeah, let's say, okay, we will take it 175. We will take a look at the material and get rid of the Poisson's ratio in order not to get too many effects to the stiffness matrix. Just for the information of you, there's generated a stiffness matrix from this thickness type, which is only having stiffness in X and Y direction of the surface. So that's how the forces are transferred. There will be no bending stiffness of, or nearly no bending stiffness, which is causing, in case there is force out of the plane, it will get a high deformation, but this can then be ignored. So it only transfers force from this edge to this edge. Okay. So then I'm defining the first selection here, or the first wall there, and this should be from this part to this part, and this to this. Did I activate all the stories? Yes, I think so. Okay. And from here to here, and here to there. Okay. This. So now my walls are defined, and I would like to add the supports on it. For the supports, I'm choosing a line support with local orientation here. And in case I'm using timber material later on, I will have to do it anyway. But I also could use a spring constant for the concrete, just to have it not statically over determined so many times. So that's also an advantage of this. Now, hold on. Maybe we do not want to see the load transfer surface, because that will just cause effects we do not want. Therefore, I'm activating the load transfer, show the reverse visibility. So this avoids that. So that looks quite good to me. yeah, and the local orientation helps also with this. Hold on. Yeah, that did not work, but okay, of course I can also delete it manually in here. This is okay. This is okay. And here on this side, that can also be. So that's, we just don't need it. It would just cause an alert. So it's not problematic, but I just want to avoid this. Okay, we go back into the Z direction. Well, we could have also looked for the supports there. That would also be possible. And the last part is the modeling of the floor. Well, we choose it rectangular to keep it simplified and define a new thickness, uniform, and floor with a dimension of optimistically 250 millimeter thickness, and go from the left top corner to the right bottom. Oh, that's not good. That we have to do again. Sorry, was too quick in selecting it. Okay, maybe zoom a little bit in, and this does not happen. Okay. So now structure is done. Each story has a mass of 172 tons. This is it. And now we have to look for the loading. Therefore, I will only activate my floor for the first load case and will define the load in it. So there I can use a simple surface load in here with a value. Hold on, I also have to look what I defined in here. So not so much load, 1.5. Oh, come on, is it not selecting it? So and on each story, I want that 1.5. All right, and it's there, and I will define two more load cases, one live load and one wind load. When I'm by defining those, I can directly say, okay, I don't want to use the combination wizard in this case. I will define that manually. Design situation, I will also look for ultimate limit state and skip all the others and define two load cases, or load combinations according first order theory. And the first one should have the mandatory or the main loading on the load case 2, so that's 1.35, added load case 1 plus 1.5, added load case 2 plus 1.05, added load case 3. I will assign that, and then do the same for the other side, but here the main loading will come from the wind load, in this case load case 3. Right, so okay, that's defined. And sorry, then it is all in, but we have to define the loads for the load case 2. Therefore, we will maybe use a little bit more force load with 2 kilonewton per square meter. Okay, and when we go here into the load transfer and not the wall, the thickness. So here I can also define the wind load with surface 2 kilonewton per square meter on the weak side of the structure, which will then be in y direction. Can move again to the z orientation, maybe though. Whoops. Right. Okay. And of course, it probably has to be minus. So that looks quite good. And it is assigned then in here. Okay. Oh, but I see it was the wrong load case where I chose it. Okay, so then we will undo this and go to the load case 3 and define it there again. Do the same. So minus. So on. Okay. Right. And all right. Cancel the visibility mode. So that's for the wind load, it works. For the live load and also for the self weight. The load transfer surfaces themselves are not such a elementary function. I said it already. For a detailed information about the load transfer surface, you have to, I have to refer for the different webinar from my colleague Niklas Wankel. But just to show you what it's doing in here, I will let the load case 3 calculate with the wind load. Okay, so that's not what I'm interested now in. What I want to show you is the load transfer in it. Therefore, here in the display navigator, via surfaces, you have the selection loads from distribution surfaces. And there you can see what it's doing. So it's transferring the horizontal force here to the edges of the floor and also to the columns. That's what it's doing here. Okay, but for the other ones, we do not have to look for the load transfer surface, and therefore we will change that by just showing the load transfer and showing the reverse visibility. And so right now, what information did I get from my building model add-on? I have the information for the, I will also skip the view of the mesh. It's not so interesting. I mean, the mesh is nice, but we're not so interested in this in here. And maybe also not show the surface cells. So I have the mass center in here, and already by this information that I have in here, I have in static analysis as a chapter or a column results by story. And there I will have, of course, the masses. Well, but not in load case 3. We would probably have to go for load case 1. Okay, so you see in load case 1, we have the masses with the load that I put onto it. I have the mass center. I have the action in each story. I have story forces that are transferred, and the location of the resultant story and the interstory drift. I have also the option to display this force graphically that's coming into it. Therefore, of course, the load case 3 can be more interesting as it shows the horizontal force in it in X, Y, and Z direction. Okay, of course, Y is in this case is more interesting. And that is this. And additionally, I have even more options with this. I can name walls that I'm more interested in. So when I take a look now at the forces, of course, we see now the deformation in here. And if we do not display the model, you can have a detailed look onto it. So deformation is really not big, but maybe when we go to the wind load, where it's, or to the load combination, where the wind load is the main guiding load. Okay, there is a little bit more load that can be seen. I said it already here, you have, because of the weak bending stiffness of the shear wall, you have some local deformations, but if you look for the local deformation, it's like a little bit turning in this direction, which of course we would like to see in here. And when we now look for the force in the surface, the shear force in each wall, you will find out that, okay, the main load is coming here on the inner wall, where of course you have the stiffening part of it. So how can we regard that? I will put the model back on, and there for this edge, and maybe also maybe this. So I have one in global X direction and maybe also this one in global Y direction. I can define in the building model add-on floor sets. They are created automatically, but I can create shear walls. So I will define shear wall in here. I can select surfaces and surface cells. Surface cells are perfect in case you want to create timber frame walls in it. But for our, right now, this is a concrete structure. It is sufficient to use the usual cells. And then I can generate a result section here. I can design it. The design properties are activated, and I can, well, of course, for it's concrete, I can do a stability analysis with the concrete add-on in it. I have the covers in here, reinforcement, and so on. But here in design configuration, that's an interesting part I wanted to show you from the building model. It is choosing the deep beams and also the shear walls from the building model add-on. And so you can, or the software, the program will automatically put the reinforcement in accordance or in relation to what is activated in the building model from this wall into this surface that I'm defining here. Okay. That's a quite important information. So we can do this on one side, and as I said, I will, as an example, also do it on this surface. Okay. I will also generate the result section and press OK and apply it. Well, okay, so far not much has happened in the structure as I do not have results, but you see that I have now the sections here in every story, and also a result beam is generated automatically. And via this, the design is done. And when I'm calculating the combination 2 again, then I have now the result section in here, and I can, maybe we will just look for our result sections. So we'll only display them in here. Maybe we'll skip the concrete information on it, as we are not so interested in the reinforcement in here. And so now when we activate the resultant, and let's say we will choose the, now maybe the section on top of each of this, oh, sorry, that's the wrong one, of this, I have now on the top story of it, I have the vertical force, then additionally for the wall underneath this, the next one, and also the horizontal force. So all the force I can have graphically in here. I have the section of it, and I have the member forces in it, so I can also see the normal force in it here, so 127.5 kilonewton I have here in the graphic. And let me show, I think the previous visibility will work. Yeah. So I have all this graphic output of it, and I get now the additional information about the forces in the shear wall that register, or this column I did not have before, and also the member forces in the shear wall. And here in the member forces and shear wall, you also get additional information for the compression and stability. So what the critical compression load compared to the force that's putting onto it is in relation. So you see, we are far away from any problematic critical stability issue. So that is just an indicator that can be prepared a lot of more force into it. Okay, so this is the information you will get by the building model without changing the floor modeling. Now, what happens when we change the building stories modeling to the already mentioned rigid diaphragm? So first of all, when I activate rigid diaphragm in here, the nodal support modeling can be chosen or defined, but I will keep it now with fixed hinge support and select OK, and it requires that the mesh is deleted, of course. So, and then from the mass center of the building model. To each FE element of my structure is defined a spider connector, or it is named, hold on, rigid links inside. I will skip the showing of it because it's not so interesting, but it is important for the modeling. And when we select now one of the stories, or maybe even better, if we look now for the building model in the data navigator, you see that additional floor sets are defined in here. And this is overwritten into our story. So there was a stiffness type standard, and this is now overwritten by floor slab rigid diaphragm, and there's chosen the load transfer distribution isotropic FEA. And similar to the facade walls that I defined, you can also choose stripes method, with what I will do now for just showing you what this means. Hold on, select them, edit, and I would choose XY stripes and uniform. And this is one of the advantages or new advantages of the building model add-on, that before a few weeks it was not possible to define a facade wall with a load transfer and a floor with load transfer. It was just not possible. And this is now possible in here. Okay, so far that's the only difference. And we can also calculate the results of the combination too. So I don't know if you saw it, but there were actually done 3 kinds of calculations. And in connection with this, I have also 3 types of analysis results. I have here in the data navigator on the top, I have walls, floors, and walls and floors global local calculation. The walls itself, they do calculate the forces in my walls, and I have the results by stories in here in order to put the output out of it. Additionally, I have here the center of rigidity in it. So when we skip this and maybe go into this view, you see that we have the mass center. Maybe we will also skip the result sections in here. And I'm not so interested in this now. And activate here on the bottom in the data, in the result navigator, the center of rigidity. And then you see that the stiffness is different from the mass center, of course, because it is on the left part of the structure, as this is the part with my stiffening elements in here. And here I only have the load transfer surfaces, and I have the walls that do not transfer any shear force, and these columns here, they also do not contain any stiffness in horizontal direction, either Y or X direction of the structure. All right, maybe we can also get rid of the grid on it. So, okay, and then, so you get this informations and also this informations in here. This is all important for the walls. I will activate the global deformation in here. Yeah, we have this little local point in there, but that's not so important. And here I have my shear forces inside, that is the important information I'm receiving from this. And then that's the information of the walls. Here I have the information of the floors. There, of course, NXY is not an important information of it, but here I want to look for the bending forces in the floors and also the deformations of it. So that's when you design the structure with each position separately, this is what you will do there as well. So we have separated or reduced the number of results here for these floors. And then the third one is walls and floors in the local, in the global local calculation of it. On the floors, I think it's easier to show what it does, what this load transfer, so this override, again, line, sorry, what this load transfer is doing in here. So we maybe look for the self-weight of it, and you see that now the loads from distribution forces, so the 1.5 kilonewton, is separated via this load transfer to each part of this. So this is how this is done in here. I have also prepared a detailed example what is done in the background of it, but before I do so, I will, as this was just for showing you what it's doing. So it's using the force from the 1.5 and saying, okay, 7.96 I get from this story, and I put here to the wall and directly on the one underneath, and so on. That's how the building model, or the intelligence of the building model add-on works. Okay, I will go back to isotropic, as this is the quicker and better load transfer direction type. And I will, before I show you the internal submodel that is generated during this process, I will just, for your information, hold on, what we will do, we'll go to the combination and look for the deformation in X direction. So you see that now the force is really different that is transferred in here. I would like to also take a look to the self-weight of it. So, okay, and now I'm changing it, and I will look for the, why do I go that 0? So we have to go for the walls. Oh no, maybe we'll take walls and floors calculation and not display the shear free walls in it. So we have here a deformation of 10 millimeters, and here let's say we will choose this one. That's probably something. So the wind is blowing in this direction. So when we put it a little bit more in this Okay, so you see that it's moving out of this plane area. Okay, maybe notes can be shown, and also members and lines, of course. Why is it not doing this? So here, this one's, and notes also. Okay, so you see now the deformation, and now I'm changing the nodal and the line support modeling in the rigid diaphragm, and I would like to choose the type. What do I want to choose? I think I choose hinge rigid, and here also hinge rigid. Okay, I think it was this amount, but it is not that important. I will show later on what this is causing. Okay, so we can actually not show this deformation, and you see that because of my modeling, I don't, I have, well, the deformation is not changing that much, but before I had 0.5 millimeters, and now I have 0.8 millimeters. So the structure is less stiff. So what did the software do now with this here? And therefore, I have this different model that I would like to show you. And I would put this on this side and this one on the right side and show you what this is doing. So I have here modeled three types of sub or models that how the software is separating the force into it. So this one is the most the first definition that I did in here. So when we go back to this one building story and say, okay, rigid and also fixed for all definitions, it's again deleting the mesh, and we look for the load case 1 with the results on it. And here we will also look for the load case 1 with the force on it. So you see here in load case 1, we have the weight of it, or maybe we will go to the load case 2. Actually, I think that is better because we do not have the self weight of the quite heavy concrete in it. You see, I have here the very stiff surface. For your information, it's always possible to see the stiffness matrix in this, and each point here is modeled with a support, each story. Okay, I said it, I want to have it on load case 2. Okay, and now I'm activating here for the load case 2 my load in it, and also let the load case 2 of this structure calculate. Okay, and look for the reaction forces. So now that we've calculated this, I think actually, let me maybe reduce the decimal places a little bit of the result. Just regarded that now is probably too much, not so important in here, but yeah, it can be a little bit confusing. So if you look for this, you see that here what is done in the global 3D model is the force that's separated via the load transfer function is what I receive as a result in this model that I created. And this is, as I said it already, is containing the supports hinged here on every part and a very stiff stiffness matrix. And now the question was, how is it changing this submodel when I change the building stories in here from a little bit out from fixed to elastic column hinge rigid, and of course also for elastic wall hinge rigid. That was the example. Therefore, I created a different example. It's called submodel rigid 2. And there you see, first of all, okay, the surface, that's the same. It's the same stiffness, so very stiff in here. But the difference here is that the line supports and the nodal supports are now changed. Then they have a spring constant, linear, and this is defined now with this spring constant. And that is exactly what is done when you change the nodal support and the line support modeling in here. It's taking the wall width, which is 20 centimeters, the height of the story is 3 meters, and because of this material, it's calculating this stiffness in here. And as you see, it's hinge rigid, just what I defined in here. I can also look for the columns. If you remember, for the columns, we choose the, hold on, cancel, don't want to change it now. So if you remember, it has this dimension, 275 millimeters thickness, Baubuche material. And when we added the nodal support in here, you can see that also these dimensions are transferred into this submodel. Okay, that is, hold on, cancel, don't want to define, okay. That is the intelligence of the building model. Now what happens when you say, okay, I don't want to calculate with concrete, I want to calculate with timber material because it's a nicer, much more nicer material, more ecologic and also more economic to be used. How can this be done? Let me first of all get rid of the transfer surface again. The load transfer surfaces. So imagine we say, okay, we don't want this shear wall type shear free here anymore. We want to have CLT here inside. So we change that and say, okay, this will now be a we can remake it, and it will be layers, and we go into the database and say, okay, I'm choosing a quite thin 5-layered thickness CLT plate, change it. And of course, I'm not doing this now in completeness, but now the floor should also have couplings inside here, because this is about roundabout, let me take a dimension line into it. Hold on. From this edge to this edge of 50 meters. So that can be produced and also brought to the job site, but not for the complete width. So there has to be some kind of connection in it, and this has to be regarded. That does not work with the rigid definition in it. So if you remember, here are defined rigid links into each edge. So how can this be regarded in here? And this can be regarded by the building model add-on with the floor modeling semi-rigid diaphragm. So there's not visible any change, but here you see in the stiffness type, there's the semi-rigid diaphragm used, and well, the load transfer is more or less the same. And here I don't have rigid links anymore. And when I calculate now again the combination 2, so okay, and now you see that it cannot be compared 100% to before, but now the floor is not so stiff anymore. I have now a higher deformation of the floor in the either walls and floors, and also walls designed. The floor itself for vertical, that's nearly the same, at least the qualitative deformation look the same. Also the output informations is also still the same. But as I said, now it is semi-rigid. And how is semi-rigid done? I made again a model for this here to compare it. That's called semi-load transfer hierarchy. And so the supports, I changed them, or I did not change them. I left them on rigid, not on rigid. Hold on, how's it named? I left them on fixed hinge support, but here the complete stiffness is chosen as it has been defined in here. Okay, I hope you gained some valuable information from this webinar. Just let me summarize what, from my point of view, was important, or I wanted to show you, is that now with the hierarchy transfer, it is possible to use also or to design or use facade elements and put, for example, the wind load for more complex structures directly to your structure. The semi-rigid diaphragm is a function where you can also regard couplings either in concrete or CLT floors and decks. The stiffness center of the structure is different than the mass center, and the output of the either reinforced or not reinforced concrete or timber walls are possible via the design configurations. Thank you for your attention, and I give back to Andreas.
Thank you, Bastian, for your nice presentation. I have an additional hint for you. Our Easter special offer is valid until tomorrow. You can get a discount between 50 and 60% on all our courses. For example, FM6, Eurocode 2, Eurocode 3, Eurocode 5, and also for the course packages 1 or 2. Just scan the QR code here above, or you can click on that field with a link for more information and to get the special offer. Okay, maybe further hint, you can download the slides from the same page where you can find the recording and the model. In the next days, you will get an email with a link to that page. Okay, that should be also all from my side. I thank you for your attention. Thanks to Bastian for your presentation. I hope we meet each other in the future webinar. See you. Bye-bye.